Hello, my name is Kylie Bain, and this is my Lab 5 video report, Choose an Adventure for Physics 2211. So I chose the rope swing in Corona Arch in Moab, Utah, because I've been there and it's a really, really cool place. Unfortunately, this is the only picture I have of me at the arch, my sister and I taking a tragic picture of holding it up. Anyway, to introduce the lab, my goal is to observe the motion of the rope swing and model it in GlowScript, and then the purpose is to see how drag affects the swing and how air resistance changes the model. We need to note that we're going to treat the ropes as a spring because they are very, very flexible, and that there's no high enough quality video to put in Tracker, so I'm not doing that, but I got a lot of information off of the internet and a behind the scenes video that I'll use to put into GlowScript. So the physics principles that we're going to use are Hooke's law, force of the spring equals negative spring constant times the length of the spring, Newton's second law, which is the final velocity is the initial velocity plus the net force over the mass times delta T, and that's just an expanded version of F equals ma. And then also the energy principles, which say the change in energy is equal to the work, which is equal to the sum of the kinetic energy, gravitational potential energy, and spring potential energy, and those are equal to 0 if the system is closed. And then we know that the equations for gravitational potential energy is mgy, and then spring potential energy is 1/2 ks squared. Kinetic energy is 1/2 mv squared. So the data that I got off the internet to use is the length of the rope was 45 meters. The distance above the ground at the lowest point was 3 meters. The spring constant I found for climbing ropes is about 10,280 Newton meters. The mass of an average human is 70 kilograms. The free fall height that they said in the background video was 39.5 meters, and the period of one swing was 20 seconds. So this is my GlowScript code. A lot of this first picture is code that I had to get to make the graphs, and I just used it from past starter codes that we've had. And then I put in a bunch of information about the balls, or like I put ball, but it's really the human's mass, position, and velocity, inputted all of those numbers in lines 33 through 39 that I had on the last slide. And then the second picture is defining all of the equations and defining initial conditions, F grav, F spring, F net, and then updating the ball's velocity, or the person's velocity, and the person's position, and getting all the information we need for Hooke's law and the energy principles. And then in line 69 through 76, I define all of those forces that we use for the energy principle. And then I'll show you the graphs that it makes. Oh, this at the end is just the arrows to show on the graph, or on the graph, yeah. And then, so here are the results. This first picture is the model without drag, which looks really perfect and nice. That is showing potential energy and kinetic energy, and then the orange line is total energy, which we see that it upholds the energy principle because the total energy is 0. And then the second picture is with drag. You can see that the period of one swing is shorter, or it changes as the swing goes on, and that the forces of drag are obviously affecting the potential and kinetic energies. So that is really interesting. And then to conclude, we see that the model that takes into account drag is much different from the model that doesn't, because the period is the same, meaning that when you're swinging on a rope swing, you're not going to make it the entire height up that you did the last time. And that's because the force of drag is slowing you down. That allows for the person to slow down and eventually come to a stop rather than continuously swinging. And we can confirm that the rope swing satisfies the energy principle because the orange line in those graphs that shows total energy remained perfectly constant. Thank you.